Okay, so we are recording, and this is Durwood King with the ELC 111. This is October 1st, Thursday, October 1st. And we're in the shop doing our Zoom session. So I've got my Zoom stuff here set up on the cart. So we're going to roll around. And instead of me just doing it from the office today and you just watching me, I made it available for people to come in to the shop and make up an in-person class that we missed last week since I'm out of place at the hospital with my mother. So anyway, and I'm just going to tell you what we're doing at each board, what they've done, what they've wired, and let you see what I'm inspecting. And this is what you got coming up. Once you finish the series circuit, you move to parallel. So I'm getting ready to check this board here. Matthew and Roger, and they have got their parallel set up. Those of you that have looked at chapter 4, you know that it's parallel, not series. So here with parallel, that's just an example of it. With parallel, your power source, the power source is connected to all of the loads equally. So if this is a 12-volt power source, the 12 volts is hooked across all of the loads equally. So when you measure voltage across each one of those load resistors, you'll measure 12, 12, and 12. It's not going to split up. So they all have the voltage that they're designed to have. So if it was 120 volt, they'd all have 120 across. And then so they all have equal voltage. That's the first rule for parallel. And then the next rule will be about current, that each load, each resistor or light bulb has a separate current to it. They don't share the same current. Whatever current comes from the power source, it actually divides in thirds. You know, so if you had, say, 9 amps coming from the battery total supplying these, each one would be drawing, say, 3 amps apiece. And they had their own branch currents. And those 3 amps apiece would add it to be 9 coming from the power supply, just as an example. And then the resistance, we'll get into that later, because I have not lectured on the book yet as far as total resistance. But that resistance, instead of it adding, it's actually going to get less and less the more you put in parallel. The overall total resistance becomes less on the power source. It sees less resistance when you put more of them in parallel. And we'll get into that part in the textbook. I won't take time to do that now on resistance, so we'll hold that thought. So here we have the first lab circuit that they wired here is we have a 100 watt bulb, a 40 watt bulb, and a 60 watt bulb in parallel instead of being in series. So they all get the same, they're all going to get 120 volts across equally. And those bulbs will be at the normal full brightness that they're supposed to be, because that's what the bulbs are designed for. And you're going to find out in parallel, that's just the way you normally wire bulbs. You did it in series to illustrate the laws of series. Now, some loads in industrial equipment is wired in series. For instance, the transformer that's right here, and I'm going to move the camera. Now, when I move the camera, sometimes the video just quits. So let me just restart the video. Okay. When I bump the camera, sometimes it quits on me. Now, this transformer, for instance, is something that you're going to wire in motor controls. This is not for residential. This is not for this class or for residential, but in motor controls, when you get into start-stop stations and transformers and motor starters and all, transformers, the windings on them, you wire them in series in some cases, and in some cases you wire them in parallel, depending on if you're going to step voltage down from what's coming in, if you're going to step it down or step it up. So there are loads in industrial settings that you do wire some things in series in reality, and you're supposed to. But so that's coming later on when you take the motor control class in January. So we're going to get the camera repositioned. I'm going to trace the wiring out and let you see through the camera what I'm doing here, what they've wired. And so all 3 of these bulbs here they're going to be wired in parallel. And so we're going to verify that. So these come from the switch over here. And each one of these light fixtures have the double terminals on them. They got 2 neutrals and they have 2 highs on there. So they come in from the switch and they've landed to one of the brass terminals, and then they've tagged off of that brass one to go to the next one. So they come into here to the second one, as you can see. They came into there with a hot wire, and then they tagged off of that same one, and they're together. Those are together. That's a pair that are together, and then the brasses are paired together. So they came in from the first one hot, and then they left out of this one hot, and came on down to this one, to the brass. So each one of the bulbs is seeing the same voltage. They're not in series anymore. They're in parallel. That's the way that they're done in residential. You're going to wire everything's parallel in residential. Same thing with the neutral. The neutral came in. The neutral came in from here. He came in here and he landed that neutral on the silver screw, and it came tagged right off of that same bus bar there, that jumper there, and tagged off of this one, and went neutral here, tagged that neutral, and came to that last one. So they all get the same neutral, they all get the same hot, uninterrupted, and therefore they're parallel. Okay, so it's very simple wiring. If you've had residential, then you've already done this in ELC 113 if you've done it in there. Okay, so the wiring looks good, and we're going to turn it on and do some measurements, and we're going to let you watch the measurements through Zoom here. That's fine. So let's cut it on. Good thing about being able to record this stuff is that people can make it. It can be 4 o'clock in the morning when they do it. Well, see, some people like Renee works. She works second shift. She gets off like really late. Now, one thing you can notice here, if you're looking through Zoom, those bulbs are a whole lot brighter than they were in series, aren't they? A lot brighter. The bulbs they're full brightness, whatever the wattage is, they got full brightness, and the bulbs are happy now. They're happy campers now. They got what they want. It's it's like or full belly for us. If you get a whole plate full, not a third of a plate, then you're satisfied, right? So them bulbs are certainly satisfied right now. So let me move my card over. And let's get your meter, and we'll get our paper out, and we'll start. So we're going along here with the questions. We're going to check the main voltage coming in, and we're going to check the voltage across each one of the bulbs, 140 and a 60, and measure. You're going to see it's going to be the same voltage. So he's checking voltage right now. If you hold the meter up, we can see if you can kind of share that. Right. Can you, if you will, right. Let's move the meter up here. I can move the meter and kind of run under your arm. So he's at the main power source coming in, and he's got the 119 at the power source. You can see under where he's at. Okay, now he's going to move over. He's going to check the voltage across the first fixture. So he's just directly across that one, and you're reading the 119. You got the full voltage across that one bulb because it's parallel. Okay, now you go to the other one. So that was the first one, and now he's going to the next bulb. That's the next bulb, and you hold it right there. And we're sitting there with 119.7, and you see there, he's right across that one. So here you got the same voltage across that first one and second one like you're supposed to. So parallel is the way you would normally wire lighting circuits. And now he's across that third one. And that third one is showing 119.712. So this is a radically different than series, okay? The bulbs are satisfied. Yeah, this is the way it's done. Okay, and so for parallel, again, as we said, they get the same voltage across each one. As you can see there, it's very obvious that they do. But so your first rule for parallel is going to be whatever the source voltage is, each one of the loads gets the same thing. The voltage drop, the E total equals E1 equals E2 equals E3. You'll find that in chapter 4. That's one of your rules. And then the next part is asking to check the amp draw through each bulb. And you're going to find that that's going to be different because the resistance on each one is different. Therefore, the amps in each branch, we call those branches or legs. So each branch is going to have a separate number of amps going in there because the wattage is different on each one. Therefore, the resistance is different. So the amps are going to be different per leg. So he's going to put his amp clamp around each branch and measure. Now, one issue we've got here that you're not going to be able to do, and I didn't even tell you about this. Yeah, we've got the way that's wired. Look, we got a little problem there with you being able to measure a branch current. When you use the tabs on there that way, you're not able to separate that branch to measure the amps. So what you have to do is, seriously, so those of you watching, the only way you can measure a branch current is if you have the connection above it and have a single line going to each fixture so you can get the branch currents in there. So we got to take those two off and put them in a wire nut with a short pigtail and then run each one. Do it on these two. So that you can have, you've got to be able to get below the junction and get that one branch current there. See? So it's going to take us a minute here, not a big deal. You just get you 2 wire nuts. I forgot to mention that. Sorry about that. So those of you watching that hadn't wired this up, basically what you've got to do is when you bring your 120 from here, you've got to have 3 wires in a wire nut. You've got to have the 120 here, and then a short pigtail going to the fixture, and then your next wire going to the next junction, and you're going to split it there with three wires, one going here and one going here. Then you can measure the amps where I've got the circle draw a separate branch current with a current clamp with those single wires going to those. So it has to be you've got to have single conductors that are you can get a current clamp around per light. So you leave the neutrals in there like that, they're fine, but just the hots have to come off. Yeah. So what he's doing is he's taking the 2 hots off of that jumper bar that's on those fixtures, and he's gonna create a wire nut with 3 wires, and they're going to have a separate drop leg there for that bulb and a separate one for this, so you can check the amps. Isolate an amp check per bulb. Yeah. And don't in real life, like in house wiring, you certainly would use those double terminals. That's what they're for. But doing the measurements that we're doing, that doesn't allow you to get one branch current reading. Appreciate y'all coming in to do this. You'll be getting moving forward and getting ahead like this, and that's going to leave some money for somebody else too to There's needle nose on the car. There's needle nose right there. Yeah. There's something right here. We're doing the check. I don't think so. McGill and Esteban ran here. Anybody else in here not being checked on series? So when we finish this one, they're doing parallel right now. We finish that. I got the Zoom right now, and I've got the cord, and I'm rolling on. Nobody's joined so far. So, but I just said Benjamin was on one time and he didn't logged out. But I was walking around. I wouldn't need to be in front of it. We might have thought that. But we're recording though. See how's my battery doing? Well, I'd say we better plug it in. Yeah. I don't know, hour and 46 minutes, we're fine. While you're doing that, let me step over and inspect this. I don't want to tell me what you got. Just carry the PIP. Like a PIP. I just think, you need to show you what you've got out there. Just go straight to it. That one I did in our last ELC class, maybe second class. Because I can walk the course in summertime. What I had, I explained some of it. I went through the basics of it. And I sent you a video that we had from real call. They explained what the three numbers are. Go back and watch that. It breaks down what those three numbers are. What they said. Watch the real hard video. Watch that, and it gives you definition of what it is. That's part of it. And then if you got, I mean, you get with him, listen to that, and then I can help you. Whatever other questions you have, and I'll help you get an answer. You know, I'll tell you what I know, and I don't know, and I usually I'll find an answer. I'll find it. I will find it. Stick to the thing, and it doesn't take long either. We got the internet, man, and you can get whatever you want. I mean, get it pretty right.
Having an account with Dropper, usually if I get in the fine,
He's right. Yeah, exactly.
usually like account like that. And
That's right. And you ask them correctly, you're gonna find the best explanation from you straight from me. Yeah. Okay, those of you watching, what he's done here is, and I'll get the camera up closer so you can see what he's done. In a nutshell, what he had was he had a wire going, the 120 going straight to the fixture, one wire going straight to it, and there he jumped straight from the fixture over to this one. And there was no separated conductor that you could get around and measure with the amp clamp, because the incoming wire went straight to the fixture, and then it left straight here and went over to the other one, kind of like this. It went straight in like this, and it jumped straight over to that one like that. Now with that, you had no way to separate the current that was going to this one as far as measuring it. So you had to go in there and produce a pigtail above it so that you can measure the amps. So let's just look at what he's got here. So he took the hot wire coming in from the switch and created a pigtail with 3 wires in that wire nut, 3 black ones. He's got one separated for that load that you can get around with an amp clamp and measure the amps of that 1 wire now. A while ago, the way it was, if you'd have checked the amps, you would have actually got the amp draw of all of them by checking that. If you'd have gone around it, you would have checked, you would have got the amp draw of the whole thing. Well, the only one that was that way is the last. You could have measured that last one. It would have been a true reading for that bulb. But the other ones, like if you'd have checked it up here, it would have given you the amp reading for both of them. Because there was no separation where you have them. You would be if you had those double terminals that way. You actually would be checking for the whole branch. So now what he's done, you can see that he's checked the branch current for that one bulb. And that lines up with what you have to have for the lab to check it where I have the red rings at, okay? He's done that on both of those. He's got on the first one and the second one, he's got 3 wires, and he's got the pigtail you can measure with an amp clamp around that one. The last one is by itself already. You can measure around it. So we get started. Okay, unlock it. I forgot that this thing. Been a while since we've done classes last year. So. And there's no other classes that are doing this. This is something unique to this class. Even in residential, if you notice, we don't really go in there check the branch currents between the bulbs. You're getting way more theory in here. So anyway, the first question here, the next question is you want to check the amp draw through the 100 watt. And so what are you getting now? You get 0.8 amps right there. And if you notice on the lab sheet costs 0.855 whenever you calculate it. Well, actually, that's actually measured. That's measured. I measured that on mine. He's getting, the 0.8, which is close to what I had measured. Next one, it says you want to measure the current flow through the 40 watt bulb. And that's the next one. And he's drawing the 0.32. And I measured like 0.33 on mine first time. And we're moving on to the 60. Watt bulb is drawing 0.51 amps on the 60 watt bulb. Notice where we got around that 1 wire. And mine drew like 0.485, right at 0.5, close to what they had. So now your next question says you want to calculate total current, I1, I2, and I3. Now your currents they're not equal. In series, your current was equal on everything, right? They all share the same current. Now you got separate branch currents. So I total is going to equal I1 and I2 and I3 together. And so if you add your numbers up, Roger's doing that over there now. He's adding the numbers up. And then you're going to measure the main current, 1.63. That's on this calculator right there. Now we're going to find out when you measure the main current feeding into all of it, what do you get? So you can actually check it leaving that switch for 1.64 is the actual number of total current for these three bulbs right here, 1.64. And then you calculated what, 1.63? So that was very good. That's very close, okay? So that everything adds up like it's supposed to. All right, so what you just saw illustrated there was the second rule of parallel that says that I total equals I1 plus I2 plus I3. That's your second rule. That's different, isn't it? Everything's got branch currents, you know. So basically, the bulbs they draw what they want to be satisfied, and you know, each one, the higher the wattage, the more amps it draws, it takes more to satisfy the bulb, right? So that's what you're getting. And your measured amps, well, your calculated amps, and then your measured amps are going to be pretty close there. May not be exact, but they'll be pretty close. Next step is you're going to calculate the resistance of each bulb when they're burning. You cannot measure a hot resistance with it burning because you'll damage the ohm meter. So you cannot measure resistance of a bulb. You can measure the cold resistance with no power going straight to the bulb. But the hot resistance, we know on incandescent bulbs, it goes up whenever they're burning. So you have to do a calculation to get it. So here on the paper, we're taking the voltage coming in, and it's divided by the individual branch currents. So those currents that he measured up in here, you do the calculations there, and then do those. So. It is. You'll do that voltage divided by the different branch currents. Exactly. And let me kind of roll over here and just kind of, I want to show you what's going on here. So see what Roger's doing here. We're going to use Roger for example. He's doing his calculations here. He's taking each one of the voltages divided by the separate branch currents, and that's what you're going to do. So kind of you can round two places. Round two different places. That's fine. Third place is fine. So he's doing all that now. That's what you'll do if you hadn't done whenever you get to the lab. That's what you're in for there. He's doing that's the example how he's doing the math there. Okay. So your next thing is you're going to change out the bulbs. You're going to rotate the wattage. Let you step back through here. So we're moving the camera around here, son. So just bear with me here. And so once he does that, once he gets the individual resistors there, the way you get the R total is you've got to use the reciprocal formula that's in chapter 4. Now we haven't gone over it yet in the lecture, but this is the way it's done. You take each individual resistor that's shown in here, you put it into a formula, and you say 1 divided by R1 plus 1 divided by R2 and so on. you add the reciprocals up of each one, and when you get that total, then you take 1 divided by the total, and it gives you the final R total. And then the final R total ends up being actually less than the smallest one in the group. When you add resistors in parallel, the total resistance becomes less and less. Basically, your pipeline opens up the more parallel paths that you put in there. The more parallel paths you put in there, the power source actually sees a larger opening. It sees larger conductor size as a whole. And more pipelines open that the current can flow through, and it sees less resistance. It sees less resistance. In series, the resistances add, but in parallel, that total will actually diminish the more you put in parallel. And now you've got the reciprocal of that 1 divided by that. No, when you get the total, you got to say you have to go through when you add all the reciprocals up, you've got to say 1 divided by the total to get the final. So in other words, that right there, you say 1 divided by that.
That right there, that, which is bring that for it, like, and then the file, then, the total, and then the file that, the 1 divided by that.
Something wrong. When you did all of this here and you got a total of this, where is that number at?
There were notes right there, but no, I think.
You're supposed to be having someone in the neighborhood of 70 on total. The number that you came up with down here, you added all the reciprocals. What particular number is that? You only need to do 3. Did you do separate reciprocals? I mean, did you add all of them up and then do 1 divided, or did you say 1 divided by this equals something and 1 divided by that one? Did you get a separate reciprocal?
Well, first thing, I go to the they're adding all that.
You can't do that. You can't add them up and then do it. Individual. Okay. Now you say 1 divided by that number, and it's going to give you somewhere around 70 dollars.
That's what it is.
Right. You got 73 critical arms.
Okay. So that makes a lot more sense.
Yeah, exactly.
See, it ain't good.
Well, see, it actually is. Look,
The
one above it shows you that's what that is.
See, what it is that little thing.
No, it's not.
Yeah, I didn't.
When you look at the textbook, let's get the textbook and I'll show you. Look in chapter 4, there's a formula that says alternate method, and that's the one you want to look at. That's the one that's where it does it. It's the easiest way to do it. I don't have to take it in much. Back. Page 29 shows this. Let me show it right in here. Page 29 in your book in chapter 4, it shows you what they call an alternate method, alternate solution, and this is the best method to use. You say 1 divided by 3 ohms, 1 divided by 6, 1 divided by 8 ohms, if that's what resistances are, you know, and then once you get those reciprocals there, those 3, you add them all up and then say 1 divided by that total, and then it's gonna give you the R total of that parallel circuit. Yeah. And just so it's going to be clear to you why the resistance is getting less in parallel, let me grab something real quick. Here's something that we have to go for parallel, and everybody needs to see this, but we have not discussed in lecture, so we got to go over now. Because this, the issue of total resistance is an unusual thing, and we've got to cover this. So let's do it in an area. Let's do it right up here, so everybody can get around. Let's get the camera up here. Those of you watching on Zoom, just hang on. Don't go to sleep on me. You got to talk to people when they go to sleep. Ain't nobody watching that later. Somebody will be watching. Right. So let's get it down here like this. Yeah, everybody kind of come around and look at this parallel circuit here. Y'all remember seeing this in series on the Zoom session? This is parallel right here. They're 100 ohms a piece. Now, those of you that are watching, watch closely. This was series, one path, power coming into here, went through these 3, and then it went back up to the power source. Starts here, enters into here, goes series through, and then it goes back to your common. This is parallel. So let's separate them first so they're not connected together. And then you're going to watch something that's very unusual that's hard really to understand until you actually see it. It's hard to believe until you really see it. So let's get a meter. Let's grab us a meter. This is one of the harder things to try to wrap our head around about parallel, and it's how, as you add resistors in parallel, the total resistance goes down every time. It keeps going down before you put in there. So we've got, when we put our leads together, you know, we have like 1.2 ohms, so we're very low. Let's check this one resistor right here. And it's reading 100 and 108 ohms. Somebody write that down, 108. This is actually something that we're not using right now. We'll use. This will be fine. and then you, so we've got 108 ohms here. It's a 100 ohm resistor, but it has a 10% tolerance. It could be as low as 90 ohms, or it could be as high as 110. That silver band means 10% tolerance of the 100. Let's go to this one. 106.2 ohms. Let's put that down. Okay, and then the next one is 106.4. 106.4 ohms. Now y'all see that they do measure what they are, right? I mean, the nominal value is 100 ohms, but they're measuring all of them around 106, 108. Now watch what happens if you put two of them together in parallel. If you know in series, if you put them in series, it ends up being a little over 200 ohms, right? Two of them. Now watch. I'm going to join. These 5 holes are together down in that product board with a clip inside. So each 5 is a group. So whatever you press into those 5 holes, it's like a line, basically. So we're going to put the tops of those together and then the bottoms of those together. Right? That makes those two parallel, and they're isolated from that one. So let's check. This is about to blow your mind here. Don't let it blow. Don't start tripping on me up here. Now watch. Now you're reading what? 54 ohms. Now, why not? That's with 2 of these in parallel. Now, I want you to pull out that red jumper while I got the meter on there and watch it go right back up to what it was. It went back to 108. You see that? Now plug it back in. This is not a trick. I'm not trying to trip nobody out here. Okay. But when you put them in parallel, here's what happens. It's kind of like if you had a pump. If you had a pump and you had one pipeline coming from that pump, maybe a 1-inch PVC line coming from the pump. And what would happen is if you plumbed in another parallel line off of that pump, and you had 2 1-inch lines leaving that pump, going to say waste treatment out there, Victor, where you're at. 2 1-inch lines leaving the same pump. Now, a couple of things would happen. The pump would end up being able to have more flow rate because you've added another line in there. And when you get more flow rate going, that means that the total load out there has less resistance than one line. When you put 2 lines in parallel, the pump actually is relieved. It sees less opposition if you have 2 lines that's pulling from it, you know what I mean, in parallel. So for the pump standpoint, the pump's able to actually pump more flow rate, more gallons per minute. Now, so if the gallons per minute goes up, leaving the pump, and it will, that's the same thing as amps. Flow rate with water is like amps. If the amps goes up, then what had to happen to the resistance out there? It had to go down, and it did go down. It did go down. So when you add them in parallel, the actual power source, what it sees is it sees less ohms, less resistance. Now let's watch this. Let's put a third one in there. We're doing that. We're bringing that third one in. And,
like 25.
And now watch. This is kind of strange. 35 ohms or 37. Now look, if I go across and check, I don't care where you go at and check it, you're going to get that same R. You're going to get that R total of about a third of what it was. It's 36.7. And you're getting slightly different because of the jumpers and the little clips that are down in that board. That's giving you some variation there. And look right here. You're getting 35 ohms there, 36 point something. Let's get better connection there. 36 ohms. 35, 36.8. No matter where you go, you're going to get a third of the total. Now pull out, disconnect the last one and watch it closely. Now you jump back to 53 something on. Now pull out that second one. You'll see it go right back up. Now you're back up to 108. Y'all see that how that works? The best way to really believe it is to really see it done like this. That's the way you can believe it. What you just saw works the same way with light bulbs or heater elements or whatever you're doing at the plant. You know, you're doing your heater elements in parallel more than likely at the plant. So what happens is the total load resistance goes down and the total amps goes up from that power source. Let's say if you had 3 heater elements and they draw, 10 amps a piece. If you have one heater element, your power source would have to supply 10 amps. You put another one in there, your power source has got to supply 20 amps. You add a third one, your power source has got to supply 30 amps, right? You got to go with the breaker size, the more you put in parallel. And that's kind of that's the idea of what goes on in the bigger setting. And on your stuff that uses those big heater elements, that's exactly what goes on. The more of them you put in there, the more amp capacity you got to have coming from the source, the bigger the breaker's got to be. But the R total ends up being less. R total goes down and I total goes up. That kind of unusual. It's really hard to really understand that, but that's the way it works. But the best way I can explain it would be with the pump and piping system. The pump is feeding the manifold, and the manifold can have branch lays coming off and say separate valves. So if I can cut those branches off, leaving that pump, it's feeding different things on the farm or in the plant, and I could actually valve them in and out. If you valve two valves off and leave one on, you might have 2 gallons a minute. You open another valve up, you've got 4 gallons a minute. Open another one, you've got 6 gallons a minute. It's 2 gallons per line. So that makes sense? Okay, good. This is a small way to see it, but this is the way to understand it. I think my camera might have been moved here. Let's let you go through this one more time to watch. I'm checking for those of you watching on the screen. We got those in parallel right now at 36 ohms. Now, if you will, very carefully pull one of them out. Now it's 54 ohms for 2 of them in parallel. Now remove it again. And now you're back up to 108. Now, in general, the camera had moved. In general, watch this right here, guys. In general, here's a general rule that it shows in chapter 4. Now watch this. Where's the textbook at? The textbook shows, yeah, if your resistors are the same resistance, here's a fast way to calculate the total resistance. It's right here on page 27. You take the resistance of one of those and you divide it by however many of them that there are. So if you got 3 15 ohm resistors in parallel, you say 15 divided by 3 and it equals 5, and that's what it is on paper. That's your ideal number. Now here, what we had was we had 3 100 ohm resistors in parallel, and then the ideal number, if they were exactly 100, the ideal number would be 33.333. But you ended up around 36 ohms because these have a tolerance. So does that make sense? Mm-hmm. So that's your first rule on parallel. So you kind of get some lecture in with this because we haven't lectured this yet. But that's the way it goes if they're all the same resistance. Okay. When they're not the same resistance, like on your lab, then, well, let's see. There's another one called product over sum. Where is it at? They don't introduce that yet. Your next method would be when they're not the same, when they're different resistors, you use reciprocal method. So you take that, they show that on page on 28 and 29. On 28, it shows that you take when they're different resistors, like 100 ohm, 200 ohm, 300 ohm, whatever they are, and they're not matched. You take 1 divided by each resistor individually. 1 over 100, 1 over 200, 1 over 300, whatever it is, and you get reciprocal of each one, and then you add all of those up, and then the final number, you got to say 1 divided by the final number. This is summarized over here. So the alternate formula shows you the actual complete formula. It says 1 over the reciprocals. Okay? So this is the one you want to use when the resistors are different. This one, when you do this over here, you still got one more step you got to do. You got to say 1 over that total once you get those totals of reciprocal. Here, it actually puts a 1 over this like it's supposed to be to get that final last number. If you end up with some number that's a decimal number like 0.625 or some small number below 1, then you haven't done the last step by dividing 1 by that to get that final number. So that if there's a 1 over all of those reciprocals to give you that. And like on the lab sheet, I did it here. So on the lab sheet, I did the reciprocals of these right here. I said one over each one of them, and it became those little small numbers there. And then you add those small numbers up and say 1 divided by, well, actually those reciprocals added up to be this number. Then you say 1 over that, and it ended up giving me 72 ohms. So when there are different resistances, here's how you can know, are you in the ballpark or not? The total resistance is going to be less than the smallest one in the group. And that's a general way of knowing are you anywhere near right, is that total, that 72 ohms is less than the smallest one in the group was 141 ohms. It was 141 ohms, 363 ohms, 249 ohms, and then you ended up with an R total of 72 ohms. So it's a little bit complicated, but that's how it works. So use the alternate method on page 29 when you're doing those mixed resistors. Yeah. Does that help seeing the resistor board like that? It's really hard to believe, isn't it? It's hard to believe until you really see it. Really, when you pull the plugs on, when you pull the wires, that ends any doubt of it that it really is what it says it is. But I like the pump analogy. The pump fluid power is the best way, honestly, to look at electricity because it's a very close comparison. It is water systems and all, pumps, pressure and all. It's really good way of doing it. We got a hydraulic class coming up in January, by the way. Hydraulics and pneumatics, I'm teaching that one. So you'll learn a lot. I like that stuff. It's good. Your electricity controls that stuff. Yeah, it runs like that. Absolutely. Okay. So we worked in some lecture here that we hadn't done yet, and that's there's a lot to wrap your head around there. There's a lot of paperwork involved in there. So when you do it, show all your math in there. There's a lot of little numbers in there, but I need to see it. It's what you did. So. It's the most number intensive calculations you're going to do in this class. So with the longest numbers. The board, yeah. If you want to experiment with it with the home meter, go right ahead. The best way is to put your hands on it. The best way is to put your hands on it. It really is. Okay, so we go back over here. We're going to finish up your measurements. So you're changing your bulbs to some other values. When you get below here, you're replacing the 40 watt with a 75.
I got to go.
Okay.
I'll see you on Monday.
Okay. Have a good weekend. So here on the paper, it says that to replace the 40 watt with a 75 watt. So you're going to end up having this on the next page, a 100, 75, and a 60 in parallel. You're going to see the branch current change here. It's not going to change anything else. And your I total will change. And then your R total will also change. So there's a 75 in there now. You see a little difference in that middle one there. It's 75. And so you just simply going to start out and check the voltage at the power source, check your individual voltage drops again, and then check your individual currents through each bulb. Yeah, I'll hold the meter for you. You're going to check the voltage at the power source at the power strip. Yeah, main power, and then each voltage drop. So you're checking main power over the strip, and it's getting 119.1 coming in, and that is going to check it at each fixture. So he's across the terminals on the first bulb. He's got 119.0. He's going to the second fixture, going directly across those terminals there. And now he's got exactly 119. To see there, this is a lot different in series. These bulbs are getting what they want now. He's across that last one, and now he's getting 119. It's exactly, if you notice, you get the exact same voltage on all three bulbs, and that's the way bulbs really want it. That's what the bulbs want. They're happy now. They're satisfied. They're burning nice and bright. And but what is different, so is the current per bulb is going to be different. The amp draw. Okay, so you're going to measure the amp draw of the 100 watt by using the current clamp. So again, the probes are used to check voltage or resistance, and now the clamp is used to pick up magnetic field. The amp draw is sensed with a magnetic field. So 0.8, and then on the one I did on mine a few years ago, it was 0.8, so that's very, very close. Next page is asking for the current draw of the 75 watt of the one in the middle. So he's drawing what? 0.54, okay. And mine, the one I did way back, was about 0.59, 0.51, and I was like 0.48. So you see that as the wattage goes down, the current goes down. You know, you went from, your first amp draw was, like on mine, it was like 0.82 on the 100 watt. And then the 75 watt, a little less, 0.59, and then the 60 watt, 0.48 amps. And that's because the resistance is different. It changes. The resistance is higher on lower wattage bulbs. They draw less amps, with more resistance. You're going to calculate total current by adding up those real numbers that you had there, those branch currents. You add those up and get a high total for number 34. That's going to give you the real a calculation from the real numbers. And then you'll put your amp probe, your current probe, up at the main power source and see does that match. So you're getting it from, you're measuring total current now where the switch is, and that's going to give you the representation there. You're getting 1.87 amps. We'll find out how close is that to your, when you added up the branch currents. It should be very close. It may be identical. Well, 34 is where you add the numbers up, and then 36 is where you actually measure. That's what he just did. 1.85, 1.87. So it's within like 10 hundredths, within 2 hundredths of a volt of amp of each other. That's good. So the next thing is you're gonna you can do the calculations. Is you're going to do E over I, the voltage with each branch current to calculate your resistances. Once you get the individual R's, you're going to do the reciprocal method again and get an R total. Now there's a lot involved, a lot of numbers involved, but you need to show them. Right. Just for sake of time, let's go ahead and flip. Change the bulb again so we can get these over there waiting on us. So you know what to do as far as the calculations there. Do it reciprocal like this. Yeah. Okay. Now you replace the 100 with a 40. We'll try to get that difference there. Time kind of flies. You got a little time to do it. Actually, you were actually, how much time? Yeah, you had to kind of a little bit. Yeah. He actually the series, yeah, we can do, yeah. So we're gonna go straight as soon as we get this measurement, we're gonna cut it off, and we'll go ahead and check it. So he's on the third section where he's changed the 100 watt with a 40. So now you've got a 40, a 75, and you've got a 60. Voltage drops are going to be the same thing across each one. You see. He's checking across that first one. He's getting the 119.2. 119.2. The next one, the 75 watts, going across it. And you've got the 119.2. The third bulb. Is across that last one, and it's 119.2. It's exactly the same. Same exact bulb, same voltage, and that's going to check the branch currents. And that's going to be the difference. It's always remember in parallel, your branch currents are going to be different per leg. .32 amps on the 40 watt, and then the higher you go in wattage, the amps are going to go up. 0.54, that's on the 75 watt. And I think this is a 60 watt here. It's going to be just a pinch less. Just a pinch less. What was it? 0.5 even on the last one. So that current went down slightly from 75. Well, I don't see it. This is the clear. There we go. 1.4. I'm just trying to, when you're doing videography like we're doing here, you got to be, it's a little challenge here, okay? That's all your measurements. We'll cut that off. So we're going to move over now. They're going to do the rest of the calculations. Now, after when you get to the last page, there's a worksheet to do on parallel. This you put your 3 rules for parallel, and you do your calculations. So let's I'll check yours if you got time. I'll check it. I understand. Okay. Let me sign in front of your paper there. At least you're here. And we got all the discussion we work our way. And it's fine. I kind of would rather do it like this. Honestly, I would rather do it. What we can start doing is doing it this way. Both days a week, those days you can get in here, I'm still going to Zoom. And then it's going to be a better blend. You've got a chance if you can get in here, you're going to get more out of it. Great. Have a nice weekend. Yeah, thanks for coming. Okay, so we're going to shift over now, and Victor's got series we're going to check. So let me move my camera around. You have to kind of bear with me on all this moving around here. I've got my Zoom card here on wheels. And I'm zooming here. We're rolling here. Very good. Thank God we can do this. And we've already looked at his wiring on series, and it is correct. He's tying his power source in. Okay, yeah, you're ready. This is stuff I want to know. We did a lot of circuit builds back in the 80s. That's what was there. You get all the theory for sure with that. My goal was to be a bench technician doing like circuit board. That's what I thought. There's not too people over there, but it's hard to find work. I know work that safety is doing. Really ends up going industrial electronics, which just like look forward to that. Switch swap it out, get a sensor or nothing. There's not much time doing. Okay, so. Yeah, so do you have a lab sheet or not? You need a lab sheet? Yeah. Okay, what you want? I think we're also going to do a both days a week like this instead of me sitting in the office doing it. And whoever can come, whoever can, watch the recording. You're getting the blend of both. So it didn't even dawn on me till, I don't know who had mentioned it, and I was thinking, well, you can't come, I'll bring the camera down here. So you start out with a 100, a 40, and a 75. 100, 40, and 75. There's a 40. That's a 60. That looks like a 75 there. You actually need a 75. What am I doing? I got a 75, Vader. Just need 100. Yep. There was a few back around here. The leather keeps you from puncturing the rubber. Yeah. But the leather is not rated for all this, but it's just abrasion like that. It's so easy to contaminate or puncture that rubber and get one pinhole in there. I've heard somebody with a power company get killed, I think, over a pinhole. You're talking way up, 13,200 above, Okay, so let's get our camera up here. Now, with his, it's coming from the switch, and it goes into one bulb with a hot, and he leaves with a hot. So it's hot in and hot out. And then the second one, it's hot going in, hot going out. You get to the last one, it's hot going in, and then the neutral coming out, going back to the power source, which is this. You got your hot coming from the power source to the ammeter, and then it goes in hot, leaves hot, goes in hot, leaves hot, goes in hot, leaves neutral, and then goes back to the source. So one pass of current there. Okay. So first thing it's asking for is we're going to check the main current coming in for the whole circuit, and then we're going to measure voltage drop across each bulb.
I think I've done that before.
Series. Well, it didn't even get wired for the other day.
Maybe I did parallel?
Series. This wasn't even wired until McGill and Esteban wired it the other day. Nobody had wired
Maybe
it.
I did two. What was the other one?
One. It was one bulb, yeah. Have a good weekend.
Never mind.
Yeah. When I was getting ready to come over here, and I said, "Do y'all have it wired?" And they looked at me, and I said, "Well, have you done series?" And they said,
Maybe it was just one bulb that we had.
It was one bulb, yeah. It was. You were changing it on one, yeah. Yeah. See, with this, that's your circuit right there, and it hadn't been done over here. Yeah. So you'll turn it on, and you'll get your amp draw for the whole thing. Mm-hmm. Yeah. I bet Russ will still be a consultant for y'all.
Yeah.
You can actually pick anywhere you want to in there. Now, you're going to see it's unusual because they're not getting full voltage across. So it's not supposed to look normal. Let me get my camera kind of quit on me.
0.26.
Sorry about the video there. So you're getting what now?
0.26.
Let me show that. 0.26 amps for the whole series circuit. Okay. And we're going to jot that down. I'm going to write numbers down for you. Now you can read the voltage drop across each one. There's going to be some odd numbers. So here you got 120 volts coming in from the switch, and it's going to distribute proportionally across these three different bulbs here. You see there, you got a little bit of burning there, you got a little bit burning there, and almost none there. You can't even hardly tell it. There's current going through it. You got to measure voltage across each one, directly across each one. You're measuring voltage drop across one. Yeah. Now let me get the meter over here, all right? I'll shut up and too. Okay. So he's checking voltage across the first one, and it's so dim that you can't even tell it's even lit at all. But there's a little bit of current going through there, and he's got 9.7 volts, not 120, but 9.7, which is nowhere near enough. Check that again. That seems odd there. Yeah, well, not 9.9. Let's use 9.9. Well, my number was a little bigger than that. But let's find out if the total is 120, and it should be. So now you check across that one. The second one, which should be the 40 watt. And you're getting 83.8 volts. 83.8. I'm going to write that down. And then across the 75, he's checking that. So he's going there, and you get 26 volts. Okay. Okay, so let's see. let's make sure that our numbers are adding up right to equal. Go back and measure your source and let's see what that is. So we're going to add the actual measured numbers up here of 9.9 plus 83.8 plus 26 volts, and it equals 119.7. And he's reading a real number of 120 volt at the power source right now. He's way over at the power source now, checking it. He's way over there checking that. He's got 120 there, 119.9. We're within like two tenths of a volt, which is fine. So your numbers are fine. You see that? It seems so odd, and it is. You would never wire that like that in the house. You don't do it that way. But in the plant now, you wire transformer windings in series if it's going to be 480 series. Parallel if it's 240, right? So this stuff is kind of giving you the baseline theory behind what you do in the industrial. Mm-hmm. Okay. There you go. Exactly. But y'all see the numbers that they're going to add up to be that source. That's just the way it is. Okay. So that's E total right there. These numbers are going to be used on the next page. So we'll go ahead and put them in while we're here. It wants to know I'm right over in here. So we'll put in that total was 119.7. Okay. We'll go ahead and include that. Just it's in there. Now you're going to calculate the resistance with them burning, of what they are. So you're going to take that voltage there, 9.9 volts divided by the 0.26 amps. And then the 83.8 volts divided by the same amps, 0.26. And then the 26 volts divided by, I'm sorry, 0.26, yeah, 0.26 amps. And we'll run these real quick in this set here. So 9.9 divided by 0.26 is going to give us 38 point, we'll round out to 38.008. 38.08 ohms. Let's double check that again. 9.9 divided by 0.26. That's right. And then the 83.8 volts divided by 0.26 amps would be 322.3 ohms. Now, why is that so much higher? Okay, it's because it's burning brighter. Okay, it's burning brighter. Okay, way brighter than what the other one is. It doesn't take as much volt. Well, let's say this. That bulb has more resistance, and in this case, you're getting a higher voltage drop across it. And it's going to proportionally be a brighter light when there's not enough voltage to go around. Okay, when there's not enough to go around, there's not in this case. There's supposed to be 120 across each one, like in parallel, but there's not. So when there's not enough to go around, the one that gets the most, shows the most being satisfied, would be the smallest one bulb. When you're running short the way we are here, that's kind of the way it works out. The one with a smaller stomach basically ends up with being more satisfied, kind of put it that way. And then the 26 volts divided by 0.26 amps is going to be 100 ohms. Okay, so that's giving you that, and then you would add up all of those R's to give you R total, which would be 100 plus 322.3 3 plus 38.08 would be 460 ohms, 460.38 ohms. That's your R total right now that I'm burning in the state that they're in right now. And it ain't normal for house lines by no means, but that's what it is. Then you take that R total, you take this E total, which would be the 119.7, divided by that R total of 460.38 ohms. And it's going to give you a calculated I total, and we'll see is it close to your real measured I total. Okay, so we go here, show this. Okay, so 119.7 divided by 460.38 ohms, and it would be 0.26 amps. That's a calculated amp draw of 0.26 amps. And we'll see is that close to what you actually measured. It's exactly what you measured. So the measured and the calculated was exact. That's always good when it's really right on point that way. So your next section is you actually cut your lights off and change, replace the 40 with a 60. So the 40, I believe, is that one. I think so, yeah. I think I've got a 60 right here. 60 right there. So what that's going to do is it's going to change the mix a little bit here. The proportions are going to be different. We're putting the 60 in the second place here, so it's a 160 and a 75. Okay, put it on. And that's changed the whole balance of things. You see now the balance is slightly different. That 100 is still not satisfied at all. It's got a little bit of a glow, but very little, almost none. And we know that there's current going through that circuit, because if that bulb was blowed, you wouldn't have any. They would all be dead. If you unscrew it right now, look at what happens. If you unscrew it, all of them are going to die out. See that? They all die. Now screw it back in. So if that bulb really wasn't conducting any current at all, they would all be dead. If that was a bad bulb. So even though it's not glowing, it's still got current going through it. It's not enough to actually make it really glow like it wants to. I put my hand behind it. You see there is a little bit of illumination in there, very little. If this room was pitch dark, you would be able to see a little bit better, Okay? So now you measure the total current with your current plant. So he's going to pick a point to measure the total current, which would be anywhere in the circuit, and all be fine because it's the same everywhere. 0.33, okay? So we're going to go here. 0.33 for total current. And he's going to measure the voltage drop across each one of the resistors. It's going to be different. Yeah. It takes a little more effort when we're trying to record this for somebody else, but we got guys who can't come, like Jamie, Jacob. So he's getting 19.7 across that first one. 19.7. And we're going to check across the 60 watt bulb now. It's right across that one. And we're getting 59.9 volts. So 59.9. And then the 75 watt. Across this. And I like this camera, boy. You can move this thing around great. It's right across that last one. And we're getting 39.9 volts. 39.9. And so now let's find out, do those numbers, are they going to come up to be roughly that 119 that we got coming in there? Let's find out again. So we do our, let's go back. So 19.7 plus 59.9 plus 39.9 is 119.5. And that agrees with the main power source, okay? We're going to plug that number in on the next page because it's going to be asking for it. 119.5 is your E total that you use on the next page. So here he's going to, you can do this on your own time here. You can calculate the R's by saying 19.7 divided by 0.33 amps. I'll go ahead and set it up. 59.9 volts divided by the same current, 0.33. 39.9 volts divided by 0.33 amps. And you're going to get your R's and you're going to plug them all into there and then add them all up, and it's going to be that R total there, okay? Take that R total and plug it in over here, and you're going to take your 119.5 over your R total on the previous page. It's going to go into here, and it's going to give you a calculated I total, and it's going to be right in range with that 0.33 there, okay? Okay. And then now you replace the 100 watt with a 40. I've got a 40 right here. Okay. And you're going to see that proportion change again. Now look at how it's changed. Just throw the balance off. This is never, you would never wire anything like this in a house. So don't think that I'm giving you something that's totally useless to do. We're learning the rules of series and how it relates. In the book, they'll show you resistors. In the labs, we're doing it with bulbs because you get to actually see the brightness change, the proportions of how the brightness gets affected. You got a little bit of brightness there. You know, the 40 has the most. It doesn't take this. You know, it's got higher resistance and it drops more voltage. So when there's not enough voltage to go around, and there's not, then the one that ends up again being more satisfied will be that 40. When you look at all of them. So this whole lab is only for purposes of learning the rules of series and how it relates, and it's preparing you for motor controls for industrial things that actually do wire in series. You know, transformers wire in series are parallel depending on what voltage comes in, and motors wire in series parallel. And heater elements can be done that way. So this is a preparation for bigger things. Okay, so now you get your the total current. He's going to get his total amps now with this change that he's made. 0.24 amps. Okay? 0.24. And that's going to get a voltage drop across each one. That's going to be a whole different mix now. So across the 40 watt, he's got 66.4 volts. So 66.4 volts. Across the 60 watt, he's getting 32.4 volts. 32.4 volts. And then the 75 watt, he's getting 20.9. 20.9. As odd as the numbers look, those numbers are still going to come out to be, and we'll do them real quick just to prove that. So there's no confusion about this. You got the 66.4 and the 32.4 and the 20.9, and it's 119.7. It's always going to equal that source voltage. Always. It has to. So it'll be 119.7. And that number is going to plug in the next page for E total. 119.7. Out there. We actually take that 119.7 divided by our total, and you're going to get your 66.4 divided by 0.24 amps. 32.4 volts over 0.24 amps because it's the same current. And 20.9 volts over 0.24 amps. Give you those R's, add them up, give you that total, stick it under there, get you I total, and that's it. And then the rest of it is going to be is state the 3 rules for series, and then do these calculations and show your points. Once all that's done, turn it in, and this is an actual paper turning. You have to turn this in. It's one of the few things. Everything else is in Moodle except these lab sheets. Okay. Be sure to don't let that get caught yet. That's our. Yeah, there you go. Yeah, take your time. There's a lot of writing involved in there. Just take your time with it. Okay, so we're going to end this session here. Everybody else is gone. And again, thank you for watching. Jamie, Jacob, those of you, Renee, whoever's watching this that couldn't join. I'm going to offer to do this each Thursday and do the Zoom. We're going to do the Zoom like normal on Thursday, but I'm going to start doing it down here in the shop. And whoever can come, that's going to give you an advantage to get more hands-on than you would be getting one day a week. So it's an option that you can do. The college didn't plan to be in person on Thursday. But I can do a Zoom down here as well as I can do it in my office. And anybody that can come on. And if there's anybody here at all, then we'll let you do a lab. Okay, so that's pretty much up to you. It's an option. It's gives you a little bonus there to get it while you can in person. So thanks for watching, and y'all have a blessed weekend. Thank you for watching, and let me know if you have any questions. We'll be back here in the shop Tuesday again. And that's it. Have a nice weekend. Thank you. If anybody's watching the video that's not connected with the college, you can contact me, Durward King, at dking@samsoncc.edu. Be glad to give you information about a program. Be glad to talk to you about getting you enrolled in some classes. We have an industrial systems program that you get a lot of electrical, you get some mechanical, hydraulic, pneumatic, belt drive, chain drive, conveyors, gearboxes, a little bit of welding, a little bit of refrigeration. All that's in the industrial program. We also have electrical certificate you can get in a year, and it's involved with our 4 classes, electrical classes. Plus, we've got a new electrical degree, a 2-year degree in electrical systems, and a HVAC degree. So we have 3 major degrees in this area, and several certificates that you can get in about a year. So let me know if you have any questions. I'll get you information about it. Be glad to talk to you. Be glad to have you join our college and further your education and get you in a higher pay scale, improve your employment situation. If you're good mechanically and you want to get good electrically, come on out here and take our electrical classes, get that certificate or get that degree, and it's going to put you in a better position with your job, hopefully more money. So anyway, thank you again for watching, and let me know if you have any questions, and you have a nice weekend.